Alright, in this video we're going to focus on continuing to manifest the power of the simulation tools that we have in the modern age to derive a system of ODEs for varying concentration N stirred tanks in series. And then we're going to subsequently simulate those circulations for a given rectangular pulse of concentration. Alright, so let's go ahead and do this. Part 1 here is really easy in the system. To describe tanks, I'm just going to use an iterator J, I think, to define each tank. So, we have 20 tanks in series here, right? And this one is going to go into the top, and then the bottom is going to go into the top, and so on and so forth. So, for the first tank, tank 1, which would be J equals 1, I'm going to say that our mass balance is simply the same as it was in our last video. So dCA dt for tank 1 is going to be equal to, well, Q over V, CA into the first tank minus CA. It's fairly simple. Now for everything past that, we can derive a really simple relation. So for tank J, let's simply say that that's going to be equal to Q over V times the concentration coming into tank J, which is the concentration leaving the tank before it. So CA J minus 1 minus CA J. And so now we can find any tank. If you have N tanks, then simply plug in N for J, and you've found the concentration profile of that tank. Okay, so now comes the more complicated part here. We want to use a rectangular pulse of this concentration, 0.5 molar, to model how the system will respond to that change in concentration into the tank, right? Now, we're going to use kind of the same theoretical tank as last time, in the sense that there is potentially reaction happening within that tank, right? So if there is reaction, we can say KCA is going to be reacted similarly here, KCA per tank J, right? Okay. Now from that, we would expect our concentration to look something like this. Here's point times step 1 times step 2. And what it says here is that we're going to have some sort of rectangle that enters at 1 second and then reverts back at 2 seconds. So here is 0.1 molar, and here is 0.5 molar, and it's going to come in, and it's going to pulse up, pulse, pulse, pulse. Now, there's a lot of extra verbiage in here about this scaled time-shifted sigmoid function with scaling of 50, all of that. All that means is simply that our rectangle is going to have a little bit of curvature to it, so it's not going to be a perfect rectangle. And I'll show you what that looks like mathematically here in the code in just a moment. All right, so then we're going to construct 2 simulations here. The first will be a plot that shows each tank's response over a time distribution, and the second will show us how each tank is lining up with different time curves in there. So let's go ahead and try to do this. All right. Start with our imports as always. Integrate import solve IDP from plotly.subplots import make subplots. All right. So now we want to go ahead and put in some of the inputs given in our problem statement. So again, these are givens here. Start with things that are really easy. So we know there's 20 tanks. We also know that the total volume is going to be 1 liter, which means that the volume for each tank is simply going to be the total volume divided by N, and that should still be in liters. We have a concentration of A at steady state that's equal to 0.1 molar. And then it looks like, let's see, do we hit all our inputs here? I missed volumetric flow rate. So you can already see that the volumetric flow rate we're putting into the system is a fairly large amount compared to what the volume of each tank is going to be here, right? Okay. And then I guess, what's the best way to do this? I want to create an array of concentrations at steady state. So I guess I can say CA naught is going to be an array of shape N or 20, and then fill it with the steady state value, right? Okay, let's take a look at CA naught. So it's 20.1. Perfect. Alrighty. Okay, so now we want to go ahead and define our function for C in. Okay. And it's going to obviously be based on time. And so the goal here is to create that rectangular pulse shape in the function. So this should be a fairly easy thing to do. We're going to use the inverse of basically 1 over exponential of x minus 1. That function is going to give us kind of that sigmoid curve into the rectangle. And so, all right, let's try this. Okay, so again, with scaling of 50, let's actually take a look here at the xbit function real quick. Let me look at it. Let's see. Okay. May have missed an import here. Okay, I may have missed an import here, so let's try that. Xbit function in Python, yes. scipy.special.xbit. So from scipy.special import xbit. Okay. So now let's take a look at xbit. A logistical sigmoid function. So 1 over 1 plus negative x. Yes. Our scaling then would just be, okay, so what we're going to want to do in this function is take in t when t is equal to 1 and t when t is equal to 2. So x bit returns negative x. So we're going to have two of these functions here. Okay. Let's go ahead and put this in the return. Okay. So now there's a 50 scaling, width scaling. So we could probably put that in one of two places. I'm not exactly sure which one. It's either going to go inside this function here, or it's going to go outside. Let's try it inside this function first. Okay. All right. So the only way to check this is going to be to plot it. So let's try it. Make subplots here. See, rows equals 1, columns equals 1. Big dot update layout. We're gonna have width equals 600, height equals 400. Actually, let's make width 800. Height 400. Template equals thoughtly dark. Big dot add scatter. X equals some lin space from what, 0 to 10 with 100 points in it. Y should be C in evaluated at X. Okay, it's not going to let me do that here. So let's go ahead and define this lin space as T. And then we can say sim T, X is T, C in of T. Okay. Mode equals lines. Let's try this, see what happens. Okay. It looks like the start of something there. So you can see that it comes up at 1, then falls right back down. It is not particularly curvy. Let's take it 1 second. Yeah, I mean, looks like pulse to me. So let's go ahead and start to see what we can do here. The next thing that we're going to want to go ahead and try to do is make another plot. We're told to make one as a plot of time varying concentrations. So that actually shouldn't be too hard. We would just plot in, yeah, so dHdt. Okay, so we're going to go ahead and start by defining a function for concentration of a specific tank, and then have it plotted out. Okay, so let's go ahead and define a function here. Not dc dt maybe. That's going to take in time and concentration. 11.2. And then, okay, so the function we derived here is that concentration of tank J is going to be Q divided by B times C from the first value to the last minus C from the how do we want to do this? This is Python indexing, isn't it? Okay. So initial concentration minus, it would be C from the second tank all the way to the end. This is from the first tank all the way to the second to last tank. Right. Okay. See if it works. And then we would have to do the first tank. So DC naught then would be just this times C C in T minus C for, okay, yeah. Right. I don't know. We're going to see if this works. We're not really sure here. We're going to have to combine these. Certain of that. So we're going to concatenate DC naught and DCJ. So right now I'm operating under the assumption that there's no reaction in these tanks. There could be, so keep that in mind. And so now all we really have to do is go ahead and solve. So res equals solve IDP DC dt. Time span is going to be from what, 0 to 100. Initial conditions. So our initial condition would just be CA naught, I believe. See if that solves. Okay. Okay. The 20 array. Let's keep going. Method. Maybe these things really do matter. Okay, no. I'll make this shorter. Okay, no. Oh, well, looking at this plot, we can actually see that something's wrong right off the bat. And that is that I didn't add 0.1 in here to that function. So it's not dropping back down to 0.1. It's actually just dropping down to 0. Of course, the fix itself was not that easy, but hey. Okay. Okay. Let's see. This might actually be practice because it should be a list. Aha. Okay. So then, moving on along, what else do we want to do here? Well, let's see, we want to create a plot. So tplot equals 0 np link space 0 to 20 with 100 points in there. And then we can say that our C plot is going to be res.solve for T plot. Okay. Now fig 2, we make subplots. Drop down this update layout line. And we want to add scatter. Okay, so now it's a little tricky. So this one, we want our x-axis to be time. So we can say x equals t plot and y equals c plot. And hopefully everybody will be all right with that. Oh boy, maybe not. Maybe not. Aha. So we have a bunch of concentrations across here. Interesting. X equals T plot, Y equals C. Okay, so we got a plot. Let's see what we got. Actually didn't run long enough. That looks better. Okay. So here we are. Here's all of our tanks, concentrations versus time. So as time goes across, you can see how each tank responds. And it makes sense, of course, that we're going to see some sort of curve that looks kind of like this if you take the top concentration from each tank, right? So that concentration pulse is being distributed among all of the tanks. Obviously, it's kind of dissolving and dissipating as it spreads down the tanks. So tank 1, or tank 1 gets the highest of it, and tank 20 here gets the least of it. Awesome. So next, our goal is going to be basically to do the same thing, except this time, what we want to do is basically put concentration down the bottom and put tank down on the bottom and put concentration on the side. So I'm going to copy this down and see what we just need to change here, besides obviously all the places it says fig 3. Okay, so now instead of C, which is, well, we still want concentration there, we just want to change where our T plot is, right? So let's see here. Time. So do we have an array of times? That would be t plot. And then do we have an array of tanks? Tank is just our I. Okay, yeah, that doesn't work. NP from space 0 to 20 with 20 pieces. Okay, it doesn't work. Let's think here. So let's think. What we're going to want to do is we need some plot of, what is it? It's called fractional transversal. So actually let's make an array, I guess, of fractional transversal. Frac trans equals a lin space from what, 0 to 20, because that's how many tanks we have, with 20 points in it, right? And then let's see. We don't really need this many counters again. We could just say for I in range, what's our range here? So we want to say I is going to be our time counter. So from 0 to, how long do we run our simulation here? Here we ran 20 seconds with maybe 200 points. Then we'll add x equals frac trans, and then y would be still c, right? Well, c doesn't exist anymore. We want to hit y's plot, so that's what we call our solution here. Well, it would just be the column. We're going to iterate that. Okay, let's see what that does first. Okay, I need to go further. Aha, okay, found it. So what I just did there was I ran it for a longer time and made it less points. And so this shows all of that. So it's not showing time 200. So it's not running as long as it did before. I guess the reason for that is that our for loop here is only running from 0 to 200. So when it hits 200, it's not going to add. So we need to add the 200 value here. Y equals plot, except we just want to have the very last value here, I think. Let's see if this works. Lines, and then the name would just be time 200. Okay, let's look at time 200 and see if it makes sense. Okay, yes, it looks like it does. Nice. Okay, so thus we've done it. This plot down here again is attempting to show basically this, if you took each one of these lines and made them this axis. So tank 1 would be here, and so at each time, so at time 20, tank, obviously at time 0, it's going to look like that for everybody. And then tank 1 is going to get hit first with that pulse. Tank 2 then starts to get hit, and tank 1 starts to ramp down all the way until you start to see those last tanks are getting hit with the pulse. Right. So that's that. So again, here, what we did was we modeled what's going to happen with a unit pulse into the system, and how that's going to affect your concentration downstream if you have a series where each tank is going to affect the next one. And so now we've kind of started to simulate a little bit more material balance-y sort of stuff. In the next video, what we're going to do then is take all of that and attempt to see what happens if, instead of having now that we've created a bunch of CSTRs in series, what happens if we can now that we have a bunch of tanks in series, what happens if we make those reactors? And so what that'll do is it'll start to simulate our plugged flow reactor if we have so many in series. So we've kind of started this series idea in this video, and I hope to continue that in the next one. See you then.